Hi everyone, I'm Emmanuel Frion. I'm currently a postdoc at Western University, and today I will talk about a work that I'm doing with two people from Western, Mateo Pascual Gomez Cuetara and Francesca Vidotto. So we are working on a bouncing cosmology coming from Loop Quantum Cosmology, and in which we also have an ekpyrotic and a matter fields. The motivation comes from the fact that having a bounce is actually one of the greatest successes of LQC. It comes at no price because it's just a geometrical effect. And bouncing cosmology is actually a good complement or even an alternative to inflation to explain power spectrum. So that's a very interesting playground to work with. And we have two fields. We have a matter field, which is used to predict the power spectrum, and we have the ekpyrotic field so that we can wash away anisotropies, because usually in the contractive phase, anisotropies tend to grow very quickly. So we have a restriction that the CMB allows for nearly scaling time spectrum, and so we will have to take that into account when we are choosing our matter field. The basis of Loop Quantum Cosmology today comes from a paper by Ashtekar, Pavlovsky, and Singh in 2006, where they found a Hamiltonian that describes not only a quantum bounce, but a quantum bounce that happens at the Planck energy density. And also this bounce helps retaining all the deterministic evolution of quantum features through the deep Planckian region. So this Hamiltonian given here depends on several parameters coming from either quantum gravity, so LQG for short, in which we have the minimum area eigenvalue, which is related to three parameters, the Barbaro-Immirzi parameter and the Planck length. And we also have the critical energy density of quantum cosmology, which is also related to gamma and lambda, and which happens to be very close to the Planckian energy density. There is also a matter content, we have Hn here, which basically gives an emergent time. So this is going to play the role of clock. And in this work, and everything that has been done in LQC, as far as I know, is taken as being a scalar field. So in 2013, Wilson Ewing decided to model a matter bounce in an LQC framework. So he chose a perfect fluid as a matter content. So the matter Hamiltonian is given by this equation here, which depends on psi, the scalar field, and its momentum, keep psi. And there is also V, which is basically the volume of the universe, which can be thought as the scale factor elevated to the cube. So to model a perfect fluid, Wilson Ewing took the form of the potential given here, which was derived by Mircea in 2009. And in the case of a single fluid, this potential always reproduces a perfect fluid in the framework of LQC. So what we have is a modified Feynman equation in which we now have a new term that is scaling like rho to the square. And using these equations and assuming an equation of states that is equal to 0, so when we have a pressureless matter, we find that we have an exactly scale invariant scalar power spectrum, which is what we expect also in matter bounce scenario outside of LQC. So recently we went a bit further and trying to find an equation of state which is slightly negative, and we found that in this case we have an almost scale invariant scalar power spectrum and also a tensor power spectrum, which is also what we can expect in usual matter bounce scenario. But one thing is that the amplitude is actually very small in this case. So the critical energy density should be matched to 10 to the minus 9 as the Planckian energy density, which is very unlikely and completely different from what we expect. As I told you before, the critical energy density should be very close to the Planckian energy density. So that is very unlikely that the matter bounce can actually account for LQC. There is still an open debate though, because we don't exactly know the correspondence between LQG and LQC, so maybe this is not a problem in the end. but still being 9 orders of magnitude difference from the Planckian energy density is something that we don't really understand, and most likely and is maybe unlikely. And furthermore, Wilson Ewing did not take into account anisotropism in this model, and that motivated other persons to work on refinement of this model. In 2020, Lee, Saini, and Singh considered an ekpyrotic scalar field plus a constant dust component. Now we have two variables, the value of the ekpyrotic field and of its momentum. Now we have two variables for the matter sector, which is the value of the phi field and of its momentum. And they chose to have a potential of the following form, which was motivated by Foucault and collaborators in 2014, in which we basically have a sum of exponentials in the denominator. We have an exponential with a negative argument and an exponential with a positive argument. And in the positive exponential, we have a parameter beta, which basically controls the symmetry of the potential. And in turn, it also controls the symmetry of the bounce itself. They found, unsurprisingly, that the scalar index in this case is equal to 1, because we have a constant dust component. So that is not surprising. And the conclusion is that this model needs some refinement, and that's where we enter the game. In our current work, we have now two fields, so the ekpyrotic scalar field and a matter field with a slightly negative equation of state at the very beginning of the evolution. So now we end up with a model with 6 parameters, 2 parameters for the geometrical part and 4 parameters for the two fields. Once again, we take the potential given by Milcharik, although in this case, we only have the behavior of a perfect fluid when the field is dominating. So this is what we have at the very beginning of the evolution of the universe. So when we start with a very big universe, which is contracting, we have matter domination, and at this point, we have a perfect fluid. So I will just summarize whatever I've said in figures. So here we start with the matter dominating epoch. And okay, the universe contracts. And at some point, the ekpyrotic field starts to dominate. And here we see that we have a change in the slope of the volume of the universe. Then at some point, we have quantum gravitational corrections. And we have something very similar in expanding phase. So here I also show that we have a negative and a positive Hubble rate, which basically means that we have a bounce. So now I want to show you what the equation of state of the different fluids actually do. So we have two effective equation of states, one for the matter part in blue and one for the ekpyrotic part in orange. So we see that we start here with an almost constant equation of state. So that helps us in defining adiabatic initial conditions. That's what we want, something that is almost quasi-dust, so we don't have any creation of particles, etc. So we start with very nice initial conditions for the perturbations. So the total energy, so the total equation of state given here by W, so the red dashed line, starts following the matter part. And then when we have ekpyrotic domination, it grows very quickly to a positive equation of state, and actually it's equal to 1 up until the bounce, where at the bounce for a short period of time, we have something that goes up to 6. So this part is important because we expect it to wash away all the anisotropes. And just so you are convinced with everything I said, here we plot the energy densities. And at the very beginning, we have the energy density of the matter field, we have matter domination. And at some point, we have a crossover between the two fields, and then we have ekpyrotic domination. And we can also put everything together just so we can have a very thorough understanding of these two fluids, of this two-field model. So when we have matter domination, we have, as I said, the volume that goes like this. And when we have the domination of the equalities, we change the slope here. And this is also the change of the drastic change actually of the equation of state. Okay, so that makes sense. We understand the background very well. And for now, what we want to do is actually to study the perturbation in this model. So we want to study the perturbations from the initial state up until the end of the domination phase of the ekpyrotic field. Because it is at this point that we will need to evaluate the primordial power spectrum. So how do we do that? Well, we are working with the Hamiltonian formalism here. So what we need to do is actually to generalize Longo's formalism in the case of LQC. So in 1994, Longo showed that the dynamics is basically given by a second order Hamiltonian. And Matteo did an amazing work, which should be in the archive soon, where he generalized this approach for AQC for an arbitrary number of fields. Here I'll just show for the case of two fields, in which we find that we have gauge invariant variables. Here, for instance, for the ekpyrotic field, which depends on the field fluctuations, on the field momentum, but also on the scale factor and its momentum, and also on the metric fluctuations. So gamma 1 is the isotropic part of the metric fluctuations, and gamma 2 is the anisotropic part. And we have something similar for the matter field. And this results in two perturbed Klein-Gordon equations that are coupled. Since we are working with two fields, we have now this set of equations, which is very hard to solve. I don't even think it is possible to solve analytically. So notice that everything that we have done is classical, but the quantum corrections are contained in pi a and pi a squared. And in fact, that's something that Lee, Saini, and Singh showed in their 2020 paper, in which taking quantum gravity correction into account merely means that we need to take these answers here, 2 and 3. So we do all of that. So we do all of that numerically. And here I want to show the preliminary results that we have of the primordial power spectrum. So here we evaluate the power spectrum at the end of the ekpyrotic. So now I want to show you the power spectrum evaluated at the end of the ekpyrotic phase. And I show here that we have the power spectrum for the two different fluids, and also the curvature spectrum that I call R. So we see that for very small wave numbers, so very large wavelengths, we have a nearly scale invariant power spectrum, and at some point it starts deviating from a scale invariant behavior, which is expected. And just to convince you that we have something that is nearly scale invariant, here I can show you a close-up for the very small wave numbers, and we find that we have something that is basically red tilted. So we are very happy with this result. At the moment of recording, we haven't calculated the scalar index yet, but we are very happy with the behavior, but we are not very happy with the amplitudes because it is very large and we don't understand why. So one thing that we are thinking is that the final amplitude actually depends on how long we spent how long matter domination lasted. So we are thinking that maybe we can play with the parameters so that we can reduce the time for which we are in matter domination, which should hopefully decrease all this behavior. And we are convinced that this is a way of doing it because we did for some different values and we always obtain the same form for the power spectrum. So we still have to do that, and hopefully in a few weeks we will be done by then. And what's next is we still have to calculate the amplitude of entropic contributions, because up until now I've only talked about adiabatic contributions. And after that, we also need to calculate the tensor power spectrum. And if everything goes well, we will have to take care of anisotropies and just confirm that they are controlled in this model. And if even this is okay, ultimately, we will finally be able to use this model for our long-term plan, which is to study a dark matter candidate that is motivated by loop quantum. I will stop here, and I thank you very much for having watched this talk.